Okay, today we are going to discuss about least square approximation, okay? That will be useful for formulation of generalized Fourier series. Let's assume that we have a vector space V, and this vector space V is equipped with dot product or scalar product. That we call it V1, V2, or V dot V2. Okay? And I assume you already know what are the properties of the dot product. It has to be bilinear in V1 and V2. It has to be definite positive, and it's going to only be 0 only when V1 or V2 is equal to 0. And for example, if the vector space is Rn, we know that V1 dot V2 is defined as the sum of V1k, V2k. It is the product of the sum of the product of the components of the two vectors. Okay? Of course, if the vector space is, for example, the space of continuous functions over A and B, we can define the dot product as, for example, Fg equal integral between A and B of Ft G conjugate in delta T. Okay? And so you can see from this perspective, we can talk, we can consider a function like a vector. And we know that given the scalar product, we can define the length of vector V as the square root of V comma V. Okay, this is the length of a vector. And you also know that the dot product allows for a definition of the angle between two vectors, because we can define V1 dot V2 is given by the length of V1 times the length of V2 times the angle between the two vectors. Okay? And let's assume that here this is V1, and here we have the vector V2. Here we have the angle between the two vectors. I can define the orthogonal projection of V1 onto V2. And this orthogonal projection, if we just use the sine and cosine formulas related to a rectangular triangle, we see that this length is equal to what? Is equal to the length of V1 times cosine of theta. Okay? And of course, now this is a vector, is right? And this is just the amplitude. Indeed, this vector, we're going to call it projection of V1 onto V2. Projection of V1 onto V2. And this is a vector. The amplitude of this vector is given by this quantity here, so it's the norm V1 times cosine of theta. And then we need a direction, right? This is basically amplitude. As a direction, we put the unit vector E2 given by V2 divided the length of V2. So this is basically E2. And this reasoning, you will see where we're going. And until now, what I did here, of course, since I'm visualizing things on a 2D plane, this reasoning is good. Is exact. This reasoning is done, for R2. But of course, the formula that we get is going to be general for any vector space of any dimension, and even for vectors, even for function that can be treated as a vector. Indeed, we know that this space, the space of continuous function, is a vector space, so let's understand. Let's see how we can rewrite this. This is V1. This is V2. Well, I did a projection, 90 degrees. And this is pi of V1 onto V2, and is equal to this amplitude times the unit vector E2. And this unit vector E2, we define it as V2 divided the norm of V2. Said that, let's manipulate this expression, and let me remind you that V1, the dot product between V1 and V2, which is also can be defined as V1 dot V2, by definition is given by the length of V1, the length of V2, cosine of theta. Okay? And so this quantity here, we can rewrite it as cosine of theta V2 divided the norm of V2. So now I'm going to multiply and divide it by the norm of V2. So nothing changes. However, now we know that we know what is this guy. All of this is basically V1 dot V2. So I can write the projection of V1 onto V2 as the dot product between the two vectors divided the length of V2 squared. Okay? And this is a very general formula, of course, that allow me to compute this projection. Okay? And we can use this formula, for example, if I have a vector V, a generic vector V that belongs to our vector space. I can, and let's assume that we have a set of vectors V1, V2, Vn. We would like to express V as a linear combination of these vectors. Okay, and also we would like also to understand when this linear combination is exactly equal to V. Now I'm going to show you that if the set of vectors V1, Vn are orthogonal. Now, what does it mean, orthogonal? Orthogonal means that Vn dot product with Vn is equal to 0 when n is different than n. Then I'm going to show you that the optimal coefficient that give me the best approximation of V as a linear combination of this set of bases Vk, which we call dictionary or basis. Dictionary comes from DSP, and basis comes from mathematics. We can show that the coefficient alpha k are equal to basically the projection of V onto each single vector vk. Okay, and that's a nice formula that has applications everywhere. You will see. From this formula we can even derive the Fourier series, for example, just to tell you something. And now, said that, let's prove that the optimal coefficient that give me the best linear approximation of V in terms of this set of bases or dictionary is exactly given by this formula. And how we do that? Well, since we are engineers, the best we can do is we know how to compute derivatives. And we're gonna do the following. We would like to write V as a linear combination of a set of bases, which I'm gonna call it V1, V2, Vn. Okay, and of course, in order to do that, we want to make sure that we don't have redundant informations. So what does it mean? We need to make sure that the vk vectors are linearly independent. Okay, linearly independent. What does it mean? It means that any vector in the dictionary cannot be expressed as a linear combination of the others. And now you will see that we'll understand now what is going to be the algebraic condition that will allow us to define the concept of independency. Okay. For now, let's assume that we want found what are this coefficient alpha k. So because we have this dot product, we know how to compute lengths. Okay. So I can define the error epsilon given by the length of V minus the sum from k equal 1 to n of alpha k vk squared. And then I ask myself, please find the optimal coefficients alpha k which minimize epsilon. And we know how to do that because we are engineers, so we know how to compute derivatives. So we have to impose that the derivative of the energy of the error with respect to alpha j has to be equal to 0 for any j 1 to n. Okay? And we can carry this we can carry this, this is the sufficient condition to have a stationary point. Of course, then we need to check that this stationary point corresponds to a local minimum, and we hope that is also going to be the local, it's going to also be the absolute minimum. Okay, and now so let's derive this coefficient, but we need to rewrite this energy in a different form. So the